Today's project is to make a load tester. I have a 48 volt 65 amp hour battery here, and this battery, because it's higher voltage, it can put out a lot of power compared to a regular 12 volt battery. I need to load test this battery. I have a 4000 watt inverter here, but that's not enough. 48 volt lithium iron phosphate battery, nominal voltage is 51.2 volts. At 100 amps, that's over 5000 watts. So this inverter is not enough. So today I need to make a load tester out of these heating elements. These are from 110 volt electric stove. Each electric stove has 4 of these in there, with the exception of the Cuisinart air fryer model, which has 2 elements on the bottom and 4 elements on the top. I have disassembled 5 electric stoves, and I have a whole bunch of elements here. They are all the same length, and they all have the same output, and they are rated between 300 to 350 watts at 60 volts each. This is a different element from another stove. It looks very different from this one, but the inside is exactly the same. There is a nichrome wire that's coiled together like a spring, and that's what gets hot when it's connected to a circuit. It doesn't matter if it's AC or DC. Here you can see the prints at the end of the heating element. 60 volts, 320 watts. It's rated at 60 volts, and that's why you always see them connected together in series on one side of the stove. The other side is open circuit. I already cut it out so I can have them individually separated. But originally they are connected together on one side with a metal spoke. And the same thing applies to this element. And this is where they're connected, and I already cut them in half. Let me show you the inside of the element. That is a spring that's made of nichrome wire, nickel chromium alloy. The same nichrome wire is inside this element, except that on the outer case it has a metal tube instead of a glass tube like the other one. Inside the glass tube is empty. There's only air in here. But inside the metal tube, we got this white stuff here, and that's magnesium oxide. It acts as an insulator to prevent the coil from touching the metal tube. The battery is 48 volts, and its nominal voltage is 51.2 volts. And that's very close to the 60 volt rating of this element. So how much power does it consume when it's connected directly to the 51 volt battery? Let's find out. 4.7, 4.8 amps, so close to 5 amps for each element. Let's go ahead and try this glass tube element as well. All right, the glass element is connected. 4.6 amps, so almost exactly the same. The resistance value of the glass elements is 8.6 ohms, whereas the resistance value of the steel tube elements is 10 ohms. Alright, so this is how it's gonna go. I have disassembled all of the electric stove except one. And this one is the Cuisinart model that has 6 elements inside. You got 2 on the bottom, 4 on the top. I'm gonna go ahead and put the other 14 elements inside this stove and all connected in parallel. Let me show you an update of what I've done so far. This is the stove completely disassembled. So that's the front. I cut out a slot on this side, slot on this side, so that I can slide the heating element through. So we slide through the slot like that. This heating element has a small metal bracket at the end. I'm using this bracket to mount it on the stove like that with a self-tapping screw. And the other side of the heating element will rest on this metal bracket here, which I mounted earlier. It's just an L bracket, which I screwed on the side of the stove using self-tapping screw. One screw here, and one screw down here. And I do the same for the other side. That way the heating element will rest on these brackets on both sides. And then for the heating element on this side, I will screw it down to the bracket using self-tapping screw, and it is very secure. It's not even moved. And here is the end of the heating elements. It will stick out at the end, but it does not touch the case, and that's very important. Otherwise it will short out. And I got the same here on this side. The terminal of the heating elements has to stick out, and it should not touch the case or anything else. Now I'm just going to go ahead and continue installing the heating elements all the way to the end. I have installed all of the elements in here. Let me show you what I've got. I've got a total of 18 elements on the bottom and 4 elements on the top. These 4 elements are original from the original stove. The elements on the bottom are secured by either screws, or there is also screws on the side of the stove. So they are held on very tight and they are not going anywhere. There's an exception that the last element, there's a hole on my bracket, so I couldn't screw it down. I used a solid copper wire and tie it to the bracket, and that is quite secure. It's not going anywhere. Let me show you the sides of the elements. So all of the elements are connected in parallel, and I use a ground bar to connect all of them together. Because this ground bar is only that long, I have to connect the 2 ground bars together, so I use number 8 solid copper wire and connect the 2 ground bars together. On this side of the stove I got 2 ground bars, and that's because, let's take a look at the elements here. So most elements on one side, it has a very thick and hard steel spokes that come out like that, and that is not very flexible. On the other side, like this one here, is got a screw mount, and then it's mounted onto a flexible wire. And these are the wires, and they are quite flexible on the other side of the elements. So on this side of the stove I have to use 2 ground bars because these steel spokes are not flexible. But on the other side of the stove I only have to use 1 ground bar because I can bend all of this wire together very easily. You can see some of the elements, they have copper wires, and that's because for some of the elements I cut the steel spokes all the way to the end here. So there's not a lot of material left. So that's why I use a solid copper wire and wrap around the ends of the element, and that will make a conductor for the elements. I do the same thing on the top with these 4 elements here. These are just size 12 solid copper wire, and I just wrap them together and connect them all together, and they all go to the same ground bar. Let me show you how I connect the stove to a battery. I use number 8 strands. So these are 3 strands of number 8 wires, and they are connected in different locations on the ground bar because I want to distribute the current evenly on the ground bar. And 3 of these number 8 wires go to the same output on the terminal here, which I will connect this to the battery. And here is the other side of the ground bar. So I got the same 3 number 8 wires go to the same terminal here, and this will go to the other terminal on the battery. However, I won't be connecting these terminals directly to the battery because this is going to be over 100 amps, and at 50 volts it's over 5,000 watts. So that's going to be a lot of spark, and the spark's going to be bad enough to melt this terminal and also melt the terminal on the battery. So that is not going to be good. For safety, I'm going to need a disconnect and a DC switch, and this will serve both purposes. It's both a disconnect and a DC switch. It's rated at 250 amp DC, So it's plenty enough for this. Just look at this. This thing is ginormous. I do have some AC switches, but I cannot use AC switch on a DC circuit because DC currents produce a lot more spark than AC, and it's very unsafe to use AC switch on a DC circuit. I just put the top cover on and it still looks like a stove, and it will function as a stove. It just cooks a little bit faster. Let me show you something. If I measure the total resistance of all 22 elements on both sides, I get 0.5 ohms total for all 22 elements. Each element is about 10 ohm. So why is all 22 elements in parallel give me between 0.4 to 0.5 ohm? And this is the reason why. So to calculate the total resistance of all 22 elements, this is the formula. And if I add them all up together, 1 over RT is 2.2, or RT equals 0.45 ohm, which is exactly as I measure on the meter. Isn't science wonderful? What you calculated in theory is exactly what you get in real life. Let's put it to the test, shall we? Let me show you what I've got. 48 volt lithium iron phosphate battery, and it's currently at 53.3 volts. On the negative terminal, it goes straight to the other side of the stove. On the positive terminal, it goes to one side of the switch, and then on the other side of the switch, it goes back to the stove. Before I turn it on, let me show you my calculation. Ohm's law, right? We know it's 50 volts, and the resistance I already measured is 0.45 ohms. So the current is estimated to be 111 amp. At least that's the theory. The oven temperature is about 13 degrees Celsius right now. Let's turn it on. Wow, you see that? 110 amps. That's exactly as calculated. Is that amazing? Let me turn on the timer and let's check on the oven temperature. Oh yeah, it's already smoking. 140 and rising fast. 160, 175, 180, 190 degrees. It's rising fast and it's smoking. Check that out. That's amazing. 108 amps right now. Wow. Let's see how hot it is. 300 degrees Celsius. 340 and rising. We are less than a minute in. 390, 400 Celsius. Holy cow. Only 1 minute. Already 500 degrees Celsius. Holy. All right, we are more than 1.5 minutes in. Let's see how hot it is. Oh my God, it maxed out my thermometer. It's over 530 degrees Celsius. 106 amp right now. 2 minutes in, and my thermometer is already maxed out. I just turned off the lights and show you how hot it is inside the oven. All of the elements are glowing red hot. Oh my God, that is amazing. All right, let's turn it off. This is crazy. I'm standing about 4 or 5 feet away from the oven and I feel hot. And this room was about 13 degrees Celsius. After only 3 minutes, check this out. It's already 17 Celsius. So it raised the room temperature by 4 to 5 degrees Celsius only after 3 minutes. I want to see what happens when I connect the oven to a 12-volt battery. So here I have a 12-volt lithium iron phosphate battery. Let's turn it on. We've got 29.2 amps going to the oven, and let's turn on the timer. See how hot it gets. Slowly rising. Very, very slowly rising. It's been over 1 minute. Let's check on the temperature. 50 degrees Celsius. That's very pathetic for an oven. And the current is around 29 amps. It's been 2 minutes. And the temperature in the oven, 70 degrees Celsius. If I used a 48-volt battery, by this time the oven already reached hundreds of degrees, probably around 4,500 degrees Celsius already. But look at this. Still slowly going up to 82 Celsius. Alright, so let's turn it off. Temperature is so mild that I can just put my hand in here. It's just warm. It's not hot at all. So we got 29 amps out of a 12-volt battery. Let's double check with my old friend, Mr. Ohm. And there we go. According to Mr. Ohm, we got 27 amps, which is very close to the actual 29 amps output. So if I use a 48-volt battery, the output is going to be 5,500 watts. But if I use a 12-volt battery, the output is only 324 watts, which is only about 6% compared to a 48-volt output. What a stark contrast in power. And to get to 5,500 watts from a 12-volt battery, in this case, it's gonna be 458 amps. Your cable is gonna be this thick in diameter. It's actually impossible to achieve on a 12-volt battery. As far as current transfer, the ground bars take 100 amp like a champ. It does get warm because there is a transfer of heat from the oven to this side of the ground bar. There's also a transfer of heat from this copper and steel conductor to the ground bar. But overall, the ground bar does not get hot at all. The copper wires, they stay cold. So there you have it, a very easy to build load tester. And not only is it a load tester, I can also use it as an oven. It's still an oven. I can still cook food in it. It's also a heater. I can use it to heat my house or a camper van. It's a very useful tool indeed. Cost-wise, it cost me 5 ovens to build this. And most of them are broken or I got them from thrift store, so they are really inexpensive. Plus some money I spent on ground bars and some money on the copper wires. The switch, I didn't have to spend any money because it came from an old solar system. Total cost of this build is only about 50 bucks. And because the oven gets really hot, and it's hot enough to melt aluminum, so my next project is to use it to melt metal such as lead and aluminum. And that's going to be my next video. Until next time, thanks for watching.